Assalamu alaikum. Hello dear students. Today we will start with the second part of chapter 8, Reflection and Refraction of Waves. At the end of this video, you will be able to explain the phenomenon of reflection of waves and its characteristics. Before we start with our new objective, let's review together the objectives of the previous video. A ripple tank is an apparatus that produces waves on the surface of water in order to study their properties. A wavefront is a line or area joining points having the same displacement. A wavefront could be plane, circular, spherical, or other shapes. A wave ray represents the direction of propagation of the wave, and it is always perpendicular to the wavefronts. Let's start our lesson by observing the behavior of light rays in the adjacent animation. Note that in the case of light, a wave ray is called a light ray. We can observe that each ray bounces back at a certain angle when it hits the edge of the mirror. Let's also observe the motion of a billiard ball. What happens when the billiard ball strikes the edge of the table? It also bounces back at a certain angle. But do you think there is a relation between the angle at which it hits the table and the angle at which it bounces back? We will see. In our last example, the sound waves bounces back at a certain angle when it hits an obstacle. Similarly, when you shout in a valley, you can hear the echo of your sound. In all the previous examples, waves were bouncing back whenever they hit an obstacle. Sound bounces back off a distant cliff. Light bounces back when it hits the edge of a mirror. Actually, these phenomena are due to the reflection of waves. Then, if we have a barrier or an obstacle, and a wave hits the edge of this barrier, it bounces back in the same medium. Then the reflection of a wave is defined as the sudden change in its direction of propagation in the same medium of incidence when it hits a barrier. Note that the wave which strikes the barrier is called the incident wave, and the wave which moves away from the barrier or bounces back is called the reflected wave. This is the incident wave. It is the wave which strikes the barrier, and the one which bounces back is called the reflected wave. You will hear these names a lot, so you should memorize them. Also, you should note that each wave is represented by a set of equidistant wavefronts and a wave ray which is perpendicular to these wavefronts. In the previous part, we have observed the plane and circular waves, where the wavefronts of a plane wave are parallel straight lines and those of a circular wave are concentric circles. But what do we observe when either a plane wave or a circular wave reflects? Let's see. In this animation, we can observe an incident plane wave. It hits a barrier, then it reflects. You can observe that the wavefronts of the reflected wave are parallel straight lines. They are clear in this figure. These are the wavefronts of the incident wave, and these are the wavefronts of the reflected wave. Also, when a circular wave hits a barrier, it reflects, and you can notice that its reflection is also a circular wave. Then we can say that the reflection of a plane wave is a plane wave, and the reflection of a circular wave is a circular wave. But what about the characteristics of the reflected waves, which are mainly the frequency, the speed of propagation, and the wavelength of the wave? Let's start by remembering that the frequency f of the wave is imposed by the source of vibration. The speed v of the wave depends on the properties of the medium of propagation, which means that all waves of the same nature have the same speed in the same medium. The wavelength lambda varies with the variation of either f or v based on the relation v is equal to lambda times f. Then, we can now conclude the characteristics of the reflected wave by comparing them to those of the incident wave. We have mentioned that both the incident and the reflected wave are propagating in the same medium, then both have the same speed. V of the incident wave is equal to the speed of the reflected waves. Also, both waves are generated from the same source, then they have the same frequency. F incident is equal to F reflected. And using the relation V is equal to lambda times F, both V and F are constant, then the wavelength of the incident wave is equal to that of the reflected wave. After we have studied the characteristics of the reflected wave, let's study the laws of reflection of waves. While studying the reflection of water waves, we place a barrier in the ripple tank. Once the incident wave hits the barrier, you can notice the change in the direction of the wave fronts. Let's start by drawing a normal line perpendicular to the reflecting surface, in addition to the incident and the reflected rays, which are perpendicular to the respective wave fronts. It's clear that the angle of incidence between the incident ray and the normal is equal to the angle of reflection between the normal and the reflected ray. You can also notice that the wavelength of the incident wave is equal to the wavelength of the reflected wave. Let's take a look at another situation with another angle of incidence. You will always notice that the angle of reflection is equal to the angle of incidence. Here's another example about the reflection of light waves. As light hits the edge of the mirror, it bounces back. And always the angle of reflection is equal to the angle of incidence. Then, the first law of reflection is that the incident ray, the reflected ray, and the normal at the point of incidence all lie in the same plane. The second law of reflection is that the angle of incidence I is equal to the angle of reflection R. Our last idea in this part is about drawing the diagram of reflection of plane waves. To draw the reflected wave, you need to draw a reflected wave ray according to I equal R, parallel wave fronts such that they are perpendicular to the wave ray and separated by lambda R equal lambda I equal lambda. Before we start drawing, pause the video and prepare a notebook, a protractor, and a ruler. Let's start our drawing by the first step, R. R means a ray. We will start by drawing the incident ray with the wave fronts separated by lambda I. Here is the incident ray, and here are the wave fronts separated by lambda I or lambda. The second step is N. N means the normal. You should draw the normal, which is an imaginary line usually drawn dotted, perpendicular to the barrier at the point of incidence. This is the normal line. The third step is A. A corresponds to an angle. You should measure the angle of incidence I, which corresponds to the angle between the incident ray and the normal. We will use a protractor to measure the angle of incidence I. In this figure, the angle of incidence is approximately 49 degrees. Denote it by I. The fourth step is R. R also corresponds to a ray, but this time we are talking about the reflected ray. You should draw the reflected ray where the angle of reflection is equal to the angle of incidence. R equal I, in this case it is equal to 49 degrees. Also using a protractor, we measure 49 degrees between the normal and the reflected ray and we draw the reflected ray. Don't forget to draw the wave fronts of the reflected ray, which are also separated by the same wavelength, lambda R equal lambda I equal lambda. Now, dear students, let's practice by solving the following application. But before you start, please don't forget to pause the video and try to solve the questions by yourself. Consider a wave ray and 4 consecutive wave fronts of an incident plane wave propagating on the surface of water in a ripple tank. The wave hits a reflector. The speed of the propagating wave is v equal to 25 cm per second. Specify the phenomenon that takes place in the ripple tank. Obviously, the phenomenon is the reflection of wave, since the wave will change its direction of propagation in the same medium after hitting the reflector. What does the angle 40 degree represent? From the figure, the angle 40 degree is the angle between the incident ray and the normal. Then this angle represents the angle of incidence I. Deduce the angle between the normal and the reflected ray. Draw the reflected ray. Using the law of reflection of waves, the angle of incidence is equal to the angle of reflection is equal to 40 degrees. Use a set square to draw the reflected ray. Calculate the wavelength of the incident wave. From the figure, the distance separating 4 consecutive wavefronts is 1.5 centimeter. We have 3 lambdas between these 4 consecutive wavefronts. Then 3 lambda is equal to 1.5 centimeter. Then lambda is equal to 1.5 divided by 3 is equal to 0.5 centimeter. Does the wavelength of the reflected wave vary? Draw 3 consecutive wavefronts. To know whether the wavelength varies or not, we start by comparing the speed and the frequency of both the reflected and the incident wave. Both the incident and the reflected wave have the same speed since they are propagating in the same medium. Both of them have the same frequency since they are generated from the same source. Then using the formula V equal lambda f, both of them have the same wavelength, where lambda r is equal to lambda I is equal to 0.5 centimeter. Now using a ruler, draw 3 consecutive wavefronts where the wavefronts are perpendicular to the reflected ray and separated by 0.5 centimeter. Calculate the frequency of the wave using the relation V equal lambda f. You have V is given and lambda is equal to 0.5 centimeter, then f is equal to V divided by lambda is equal to 25 divided by 0.5 is equal to 50 Hertz. Now let's summarize together the ideas mentioned in this video. Reflection of waves is the sudden change in its direction in the same medium. The incident and the reflected wave have the same speed, same frequency, and same wavelength. The laws of reflection are: the incident ray, the normal, and the reflected ray all lie in the same plane. The angle of incidence I is equal to the angle of reflection R. Here is the incident ray, where the angle of incidence is equal to the angle of reflection, and here is the reflected ray. And this is the normal, which is perpendicular to the barrier. Thanks for your attention. The end of part